Ah, very good. This is a calculus-based class, and I expect everyone to know at least the rudiments of differential calculus. What's the function, what's the derivative, what's the second derivative, how to take derivatives of elementary functions, how to do elementary integrals. Sometime later, I will deal with functions of more than one variable, which I will briefly introduce to you, because that may not be a prerequisite, but certainly something you will learn and you may use on and off. But there are different ways of doing physics. Mine is to demonstrate over and over how little mathematics you need to get the job done. There are others who like to show you how much mathematics you could somehow insinuate into the process. Okay, there are different ways of playing the game, and some of us find great pride in finding the most simple way to understand something. That's certainly my trademark. That's how I do my research also. So if you feel there's not enough math used, I guarantee you that I certainly know enough eventually to know the whole class. But that's not the point. I will use it in moderation and use it to the best effect possible rather than use it because it is there. Okay, so I don't know your mathematical background, but the textbook has an appendix, which is a reasonable measure of how much math you should know. You got to know your trigonometry. You got to know what's the sine and what's the cosine. You cannot say, I will look it up. Your birthday and social security number is what you look up. Trigonometric functions you know all the time. Okay, I will assume you do. All right. And, of course, trigonometric identities you know from high school, pages and pages of them. So no one expects you to know all those identities. But there are a few popular ones we will use. All right. Anything else? Yes?
This may be a bit early, but when will we find out when the midterm is?
Yeah, midterm will be sometime around 20th of October. I have to find out exactly the right time. We have 24 lectures for this class, and the first 12 roughly will be part of the midterm. But after the 12th lecture, I may wait a week so that you have had time to do the problems and get the solutions. Then I will give you the midterm. Yes? Yeah, this tells you in detail. This flyer answers exactly that. Okay, there's one more question for somebody. Yes?
A few people I've talked to have recommended that we start taking the lab second semester instead of first. Would that be advisable, or should we take both concurrently?
I don't have a strong view. I think you should take the lab sometime. But I don't know how many semesters of it you have to take. But I would say the advice of your predecessors is very important. If they tell you this is what works, that's better than what somebody like me can tell you. Also, you should talk to Stephen Irons, who is the director of the labs. He has seen every possible situation. He will give you good advice. Let's start now. Okay. So we are going to be studying, in the beginning, what's called Newtonian mechanics. It's pretty remarkable that the whole edifice was set up by just one person, Newton. And he set us on the road to understanding all the natural phenomena till the year 1800 and something, when Maxwell invented the laws of electromagnetism and wrote down the famous Maxwell equation. But except for electromagnetism, the basics of mechanics, which is the motion of billiard balls and trucks and marbles and whatnot, was set up by Newton. So that's what we are going to focus on, and you will find out that the laws of physics for this entire semester certainly can be written on one of those blackboards or even half of those blackboards. And the purpose of this course is to show you over and over and over again that starting with those one or two laws, you can deduce everything. And I would encourage you to think the same way. In fact, I would encourage you to think the way physicists do, even if you don't plan to be a physicist, because that's the easiest way to do the subject. And that is to follow the reasoning behind everything I give you. And my purpose will be not to say something as a postulate, but to show you where everything comes from. And it's best for you if you try to follow the logic. That way you don't have to store too many things in your head. In the early days, when there are 4 or 5 formulas, you can memorize all of them. And you can try each one of them till something works. But after a couple of weeks, you will have 100 formulas, and you cannot memorize all of them. You cannot resort to trial and error. So you have to know the logic. So the logical way is not just the way the physicists do it. It's the easier way to do it. If there is another way that will work for non-physicists, I won't hesitate to teach it to you that way. But that turns out to be the best way. So try to follow the logic of everything. Okay, so Newtonian mechanics is our first topic. So Newtonian mechanics has two parts. Or all of physics consists of is a two-part program. The plan every time is to predict the future given the present. That's what we always do. When we do that right, we are satisfied. So the question is, what do you mean by predict the future? What do you mean by the future? What do you mean by the present? By present, we mean we will pick some part of the universe we want to study, and we will ask, what information do I need to know about that system at the initial time, like right now, in order to be able to predict the future? So, for example, if you were trying to study the motion of some object, okay, here is one example here. See, that's an example of Newtonian mechanics. I'll give you one more demonstration. Let's see who can catch this one. That's a good example. So that was Newtonian mechanics at work, because what did I do? So I released a piece of candy, threw it from my hand, and the initial condition had to do with where did I release it and with what velocity. That's what he sees with his eyes. Then that's all you really need to know. Then he knows it's going to go up, it's going to curve, follow some kind of parabola. Then his hands go there to receive it. That is verification of a prediction. His prediction was the candy is going to land here, and he put his hand there. He also knew where the candy was going to land, but he couldn't get his hand there in time. But we can always make predictions. But this is a good example of what you need to know. What is it he had to know about this object that was thrown? I claim is the initial location of the object and the initial velocity. The fact that it was blue or red is not relevant. And if I threw a gorilla at him, it doesn't matter what the color of the gorilla is, what mood it is in. These are things we don't deal with in physics. Or if there is a tall building, a standard physics problem, an object falls off a tall building. Object could be a person. So we don't ask, why is this guy ending it all today? That's not, we don't know, and we cannot deal with that. So we don't answer everything. We just want to know when he's going to hit the pavement, okay? And with what speed. So we ask very limited questions, which is why we brag about how accurately we can predict the future. So we only ask limited goals, and we are very successful in satisfying them. So we are basically dealing with inanimate objects. So the project of Newtonian mechanics of predicting the future given the present has got two parts. And one is called kinematics, and the other is called dynamics. So kinematics is a complete description of the present. It's a list of what you have to know about a system right now. For example, if you're talking about the chalk, if I throw the chalk, you will have to know where it is and how fast it's moving.